emeritus scientist from Delhi, who is also a INSA professor, and he was kind enough to give his talk on water-soluble fullerenes for the benefit of our research scholars and scientists. I am extremely happy to welcome Professor Eswaran for this presentation. Let me also welcome Dr. Velayudham, the acting director today, and invite him to preside over the function. And let me also request Dr. Velayudham to introduce Professor Eswaran to the honorable members here. Dr. Velayudham, please.
Once again, welcome all of you for this talk. Today we have Dr. Eswaran with us. He is kind enough to come here from all the way from Faridabad, Haryana, to deliver a talk on fullerenes and its applications in material science and medical area. So Dr. Eswaran is currently visiting scientist, Regional Center for Biotechnology, Faridabad. He held various positions like Emeritus Professor of ACSIR, ex-Emeritus Scientist CSIR, ex-HOD Chemistry and Dean Academic St. Stephen's College, Delhi, and ex-Principal of Deshabandhu College, University of Delhi. In addition, he held various awards like Dr. APJ Abdul Kalam Lifetime Achievement Award in 2016, INSA Teacher Award in 2013, and nominated by Dr. Sri Visveswara College, University of Delhi for a lifetime dedication to undergraduate teaching, and a Teacher Award of Eminence in 2017, CRSI Best Teacher Award 2007, and he held various awards. So with this few introduction, I request Professor Eswaran
discuss some aspects of nanocarbon materials, particularly fullerene C60. We are familiar with the word fullerene. It's also known as Buckminster fullerene. Somebody has written a book I saw yesterday in IIT Madras. The book is entitled The Most Perfect, the Most Beautiful Molecule. Some of you know it is an allotrope of carbon with spectacular properties and looks like almost a football. Sometimes people also refer to it as football-y, which is not a very appropriate or a correct name. In this talk, in the next 1 hour, I will cover two major aspects. One is, most nanocarbon materials are completely insoluble in most organic solids. If something is insoluble or has very poor solubility, very difficult to use it. So I am actually talking about this morning about water-soluble fullerenes. During the course of this 1 hour, you will realize how many papers have been published in the last few years on this topic. Water solubility brings about tremendous advantages in many fields. In the area of material science, nanocarbon materials that we know of are materials like not only Buckminster fullerene, nanotubes, carbon nanotubes, single-walled carbon nanotubes, multi-walled carbon nanotubes, graphene. We are aware of the fact that 2 Nobel Prizes have been awarded to this area. But because of their poor solubility and very high cost and toxicity, in spite of 2 Nobel Prize winners in this area, led by Professor Grotto and others, it has not led to any commercial utilization. Am I saying this alone on my own thoughts? Please access a paper published from Oxford University in 2017, which says exactly what I have said. What is the purpose of having a substance which is black in color? Okay, nano, so what? If it has no use, it has no applications. If we derivatize, functionalize these nanocarbon materials, they become less toxic or non-toxic, and they can be used for various purposes. But derivatization meant invariably you took the nanocarbon material and heated it with concentrated sulfuric acid and concentrated nitric acid. Imagine such harsh treatment. I dare say that in my method I am able to do these functionalizations under much milder conditions, therefore less or no damage to the nanocarbon material. There is a spectacular use that has come about in recent years, a new word. I don't know whether all of you are familiar with this word. Theranostics. Theranostics. Theranostics, the word arises from diagnostics plus therapy. Theranostics means diagnostics plus therapy. There is even a journal with the title Theranostics. What is the main advantage of fullerene being considered? As you will see shortly after this formal talk is over, you can precisely measure, especially by mass spectrometry, the molecular weight of these substances. They are homogeneous. Pharmaceutical industry wants things which are fully characterized and are reproducible each time. So if you know the molecular weight precisely, naturally it's a great advantage for any candidate drug that we can think of. Since I'm talking in secondary, I think it's appropriate that I highlight that these materials are candidates for solar cells. They are energetically deep-lying lumos with a very high electron affinity. The LUMO allows the molecule to be reversibly oxidized and reduced with up to 6 electrons being taken up during the reduction process. It is able to stabilize negative charge. The state-of-the-art photovoltaics, particularly the bulk heterojunctions, using the fullerene derivative phenyl butyric acid methyl ester, PCBM, is one of the most patented, one of the most well-known derivatives of fullerene. But the efficiency only reaches about 5%. Then why should we be talking about when silicon-based solar cells give you up to 20% photoconversion efficiencies? Why should one be worried about 5% converting efficient materials which are, even if they are nano. The reason is that this can lead to plastic electronics, foldable electronics, wearable electronics, meaning thereby, say, a person can have so many gadgets which are actually embedded into the dress of the person. Imagine a soldier in the Pakistan border or the Chinese border somewhere having so many such gadgets which are very small in size and which are embedded into the dress. Yet you could have a small TV set or a newspaper which you just fold like a small plastic and put it in your pocket, and whenever you're traveling somewhere, open it and read it. At the moment, I don't think we carry our huge, people have very large screens in their homes for televisions and so on. We can have plastic foldable electronics. It is appropriate that I briefly refer to my past work. We actually produced soluble fullerene derivatives, characterized them by thin layer chromatography, purified them column chromatography, preparative TLC, repeatedly, infrared spectroscopy, UV visible spectroscopy, NMR, H1, NMR spectroscopy, and what is shown here is a C13 NMR spectrum of a soluble fullerene. Fullerene has 60 carbon atoms. So its molecular weight is, help me calculate, 720. You can measure this up to the 4th decimal place. Remarkable. By mass spectrometric techniques. But one of the observations is, if you will record a 13C or C13 NMR spectrum, of course it requires 16,000 scans, so it takes computer time, instrument time, for which you have to pay. But all the 60 carbons are identical. In the original C60 molecule, there will be only one peak. But if you derivatize, you can count so many peaks. In this particular case, up to 16 peaks, and you can actually decide the symmetry of your derivatized fullerene. We have done this in the past using the soluble fullerene. It was not water soluble. Remember, it was not water soluble. We made solar cells with the CSIR laboratory, National Physical Laboratory in New Delhi. The device structure apart, the photo converting, this is the HOMO and the LUMO values. If you will see for ITO, P3HD, our derivative 1, our derivative 2, PCBM, just C60 itself and aluminium. The differences are not very large. And these two compounds here were synthesized in my laboratory. Paper published in Synthetic Metals in 2011 in collaboration with the National Physical Laboratory, the CSIR laboratory in New Delhi. At that time, to determine the HOMO and the LUMO, we carried out a cyclic voltammetry, which is reproduced from our research paper. The photo conversion efficiency was not very spectacular, but almost matched that of P3HD and PCBM, which was one of the most reported ones at that time. I understand that the photo conversion efficiency PCE may dramatically increase if the same experiments are carried out in vacuum. We have not carried out these in vacuum, we have carried out in the open laboratory. Fullerene derivatives are considered as candidates for hydrogen storage for internal combustion engines. If you see the values here, compare it with metal hydride, 12 pounds if a fullerene is used, 12 pounds if metal hydride is used. Amount of storage media required in the case of fullerene is just 197 pounds, whereas in the case of metal hydride it could be as high as 1200 pounds. So there are considerable advantages in using fullerenes, carbon nanotubes for hydrogen storage. Every possibility that in the coming future the fuel that will be used for internal combustion engines could very well be hydrogen stored in nanocarbon materials. A prospect that should especially very attractive for a laboratory like your laboratory in Karikuri. Am I right? Could be a candidate which we could consider. Last time I had shown this photograph. How many people remember or identify this photograph? Is this from Mohenjo-daro? Not at all. It is the surface of a silicon wafer etched in Kodak Laboratory in Rochester, USA, and the size of the wall here, this distance is 1 micron. Now for comparison, all of us know a human hair is 70 microns. So 1/70th is the size of this wall. This has been etched. This process has been done with my own materials, polymers made from cashew nut shell liquid and blended with photoactive compounds made by me, exposed either as a negative resist or as a positive resist, etched, and microelectronic circuits printed by me. That is the polymer I made, Tumba. That is the printing. The source was the cashew nut shell liquid, not the cashew, but the cashew nut shell liquid. And if you notice this beautifully, printed surface of silicon wafer, this is the original resist which has not been washed away because it's got cross-linked. This has been washed away, so you can get prints at micron level. I did it at 13 microns and published this Journal of Applied Polymer Science. Yes, I did get an Indian patent in 2010 in collaboration with the Ministry of Defense Laboratory Solid State Physics Lab. I hope some young persons will take up my patent and actually use the material which comes from this part of India considerably, cashew nut shell liquid, and possibly produce a polymer and produce a photoresist. But what I am interested in today is not insoluble nanocarbon materials. Focus on the use of water-soluble nanocarbon materials like fullerene. This is a paper published in 2000, I presume, in the Journal of Microelectronic Engineering in 2002. The title of the paper reads Multi-adducts of C60 for electron beam nanoresists. I mentioned to you, I have done photomicrolithography at 30 microns. You saw that figure. I am no longer talking about photomicrolithography. I am referring to the fact that one can produce multi-adducts, water-soluble fullerene derivatives using electron beam. You can print nanocircuits. If you notice, the surface of this fullerene molecule, all these green, are all carboxylic acids. If you can attach so many carboxylic acids on the surface of this nanocarbon material, it makes the exterior of the material highly polar, and therefore the material becomes water soluble. And such materials have tremendous electrical and magnetic properties, as was mentioned in the reference that I had cited. So see this. This whole distance here is 200 nanometers. What is the distance of this wall? Certainly nanolithography. And you can make nano devices. I don't know whether Dr. B.L. Fellinger, this year's Nobel laureate, has visited SECI. Once he had come to our college in 1991, he makes molecular switches. His book is entitled Molecular Switches, and he has won the Nobel Prize this year from Holland for making molecular switches, for making nano devices. How wonderful it would be if, along with whatever experience I have gained, if young people in SECI, with the professors assisting this thought, print nano circuits and make nano devices. How will you see a nano device? Will it be visible to the naked eye necessarily? If some device is made at the nano level, you may have to visualize it in other manners. Say, for example, a nano motor for that matter. In the next slide is shown a diagrammatical representation of what is possible. Here is an electrode. Here is a porphyrin wire. Here is a fullerene. Another electrode. Then cathode and then anode. And you shine light, electron transfer happens, and fullerene. When I was a student, I was taught about Avogadro number, that means 6.023 into 10 raised to the power 23 units, molecules, or whatever have you as an ensemble. Today, we have reached an age where we can talk about using a single molecule at a time and making a molecule or molecular wire. I collected these thoughts of mine mainly because this laboratory's area of focus is on electrochemistry, and I think this comes within the charter of SECI. Am I right? Such materials, such nanomaterials that I have been mentioning in the last few minutes are also used or useful as magnetic resonance imaging contrasting agents, MRI contrasting agents. There is a patent which is, if I am not mistaken, a 2016 patent, US patent. Let me read the title. Water-soluble fullerene formulations and methods of use thereof. I am extremely happy to tell you a similar patent. Water-soluble fullerenes. What have they shown these to be? They have shown water-soluble fullerenes are in fact radical oxygen scavengers, ROS. We all know oxygen is very important for us. Who doesn't know? If our brain does not receive oxygen supply or glucose supply is cut off, the man is in great danger, in deep trouble. Oxygen is absolutely essential. there is a small problem. Sometimes in our body, oxygen gets converted into radical oxygen species, like hydroxyl radical. Imagine hydrogen peroxide, H2O2, which is so corrosive, being produced in somebody's eye, a human being's eye. What will happen to the radical? These are extremely harmful to the human body. Many doctors today prescribe antioxidants over and above vitamins to which we are used to. What is the question I am asking? What causes most of the diseases? In my opinion, based on considerable amount of reading in the last 1 year, I am convinced of the fact that radical oxygen species are responsible for causing most feared and dreaded diseases. That means, that takes me to the second part of my talk. These water-soluble fullerenes, what are their medical applications? Now it may appear to you the next few minutes that some of the things I may tell you look like science fiction. But I dare say they are all facts.